Thank you very much. Thank you very much for the kind introduction. So I thought since, well, I guess about half of the audience is probabilist, but maybe the other half is not. And so I thought I'd start by, trying to explain what we probabilists actually kind of do, because when you tell sort of a non-mathematician that you study probability theory, then there's usually three kind of reactions. I mean, of course, the normal reaction is I was never good at math. But that's a sort of general reaction whenever you tell anyone you're a mathematician. So on the probability side, usually one possible reaction is to say, oh, but that's not possible because, well, if you do mathematics, it's for things that are certain somehow, whereas probability is things that are random, and so it's completely, incompatible. And that's, of course, not the case. And the other kind of reaction is something like, oh, so then you should be good at sort of predicting what the next lottery outcome is going to be, or something like that, or if it's going to rain in 3 days. And of course, we are not really better than anybody else at predicting that kind of things. And particular sort of what probabilists mainly do is, in some sense, transforming probabilities, right? And one thing which is maybe not, one reason why people sometimes get confused by probability theory, or why it's a somewhat subtle kind of thing, is that it's one mathematical theory that actually describes several different situations that are somewhat related in an intuitive sense, and it's described as the same mathematical theory, but they're actually not quite the same thing. And the other thing is that somehow, one tends to think of the probability that something happens as something somewhat intrinsic, right? Like something like the color of an object or the temperature of something. And that's not the case at all, right? So somehow if I toss a coin, and then, I look at the outcome and I ask you what's the probability that it's heads, you're going to say, well, it's 50%. But I look at it and I see that it's already heads. So for me, the probability is 100%, or 0% if it's tails, right? So the probability that something happens is actually something that also depends on the observer, right? Or the probability that something has happened is something that very much depends on the amount of information that's available to you, and the one available to you is maybe different from the one available to me or to someone else, or to your field. And so the general kind of situation that probability theory models, right, is something where you have some kind of experiment, because experiment doesn't necessarily mean like physics experiment in a lab. It means, any type of situation where you try something out, where the information that's available to you a priori before you do the experiment is not sufficient in order to actually determine the outcome. And there's some sense, generalizing a bit, there's roughly sort of two types of interpretations here. One of them is kind of objective. So if it's an experiment that you can repeat, right, with basically identical situations, then it's clear what we mean by the probability of an outcome, right? If I toss a coin, I can toss a coin 1,000,000 times, and I'm going to do it, sort of in the same way. And about half of the time it's going to come up heads, about half of the time it's going to come up tails. And so we say that the probability it comes up heads is a half, because it comes up a half of the time. But of course, there are very often in real life, we talk about probabilities for things that you cannot repeat, right? Like if you have an election next year, you're talking about what's the probability that, this party wins the election. Well, it's going to happen, and then that's it. You're not going to rerun the same election with in the same condition another time. Maybe you have an election again 5 years later, but it's going to be in a completely different context, in a different setting, so it's not the same experiment. And so in that case, what do we actually mean by a probability, right? So when you say, well, as far as I'm concerned, say the probability that this person wins the election is 30%. So what do you actually mean by this? It basically means that, you know, if you were betting on the outcome, like how much money would you be willing to put down in order to buy a ticket which gives you, say, $1 if the outcome is that that person wins the election, right? So say you have a ticket, you can buy the ticket, and then the election happens a week later. And then if the person loses, well, you've lost your money, that's it. If the person wins, then you gain $1, or say 1,000 yen. Okay? And so then, you know, how much are you willing to pay for that ticket? Right? Like if you're really certain that the person is going to win, then you're going to be willing to pay very close to 1,000 yen, right? Because like basically whatever the maximum amount you're going to be willing to pay is going to be very close to 1,000 yen because you're very certain that the person is going to win. And so having a 30% probability of winning for you basically means that you're willing to put down 30% of 1,000 yen. So you're willing to pay 300 yen for that ticket. And you think that, you know, more than that would be unfair price, would be too expensive, right? And less than that, you would be very happy to pay it because you think that on average you're going to win. So in some sense, that's also a probability, right? But it's somewhat different from, you know, the situation where you just take an experiment and you repeat it many times and then you just observe, if you want, somehow the probability of the outcome. But both of them are somehow modeled by probability theory. And then, of course, there are various rules for somehow manipulating these probabilities, which you probably know about, so that if, you know, if somehow you have two different outcomes that are mutually exclusive, then the probability that one of them happens is the sum of the probabilities that either of them happens. And if you have two independent things, then the probability that both happen is the product of the probabilities and so on, right? So you have these kind of rules for manipulating probabilities. And in some sense, that's very much what probabilists kind of do. They play with these rules, and then but then what they're kind of interested in is, well, you know, you're interested in making some kind of predictions, but since if you're only able to kind of manipulate probabilities, you still have to start from somewhere, right? And so how do you get a starting point? Well, there's basically two principles that you kind of use to get a starting point. So the first one, like in many parts of mathematics, is symmetry, right? And so the kind of symmetry here is the one, suppose that you do some experiment where you only have finitely many possible outcomes, like tossing the coin, right? There's two outcomes, basically, either heads or tail. And then suppose that you're in a situation where you can distinguish between these outcomes, right? So you can look at the coin, you see heads or tail, you can see the difference. But the mechanism that produces these outcomes doesn't distinguish between the two, right? Like if the coin is really well balanced and symmetric, as far as, you know, tossing the coin is concerned, both sides of the coin behave in the same way, right? And so in the case of the coin toss, you have two possible outcomes, but the two are completely symmetric. You can tell the difference, but the mechanism that produces the outcome cannot tell the difference between the two. And in that case, there's no reason why one of them should have a different probability than the other one, and so they have to have the same. And so since probabilities of, you know, mutually exclusive, so if you have finitely many outcomes, the sum of the probabilities for each outcome have to add up to 1. And so if they're all the same, well, each of them has to have probability 1 over the number of outcomes, right? So then you have a starting point. So that's the example sort of the coin toss, or for rolling a die, it's exactly the same thing with 6 possible outcomes, right? So you have probability 1 over 6 for each of them. The other one is a bit more subtle. So the first one, of course, it's something that we all experience in real life. We all have played games where we roll die. The second one is a little bit more subtle. And so we call it universality. It's something that probably most of you have seen because you've probably at some point or another during your studies seen the central limit theorem. Right? So I mean, obviously I'm not talking to a probalist here. So you've obviously seen the central limit theorem. And so what it says, so the central limit theorem, what it says is basically if you add up many random quantities that are sort of all roughly about the same size and that are independent, then what you're going to see, like the distribution of this sum is always going to follow kind of the same shape. Okay? So that's something that was in some sense already observed by, in the 18th century by Demois, when then, the first one to really kind of do a proper calculation to justify it was Laplace in the early 19th century, so that's kind of really an old result. So the kind of thing where you see this is, imagine here what you do is you toss a coin 100 times, and you count how many times you get head. Right? So on average, it's going to be 50, but it's not always going to be 50, right? Like sometimes it's going to be maybe 47 or 52 or something like this. It's rarely going to be 80 or 10, right? Usually it's somewhere around 50, maybe between 40 and 60 or something like this, right? And so now you do that 1,000 times, and you plot, you look at how many times did you get 50, how many times did you get 49, 51, 52, 53, and so on, right? And that's these crosses here. And you get something a bit random like this, but it sort of more or less follows some kind of shape like that. And if instead of doing it 1,000 times, you do it 10,000 times, then it sort of follows more precisely that shape. And if you do it 100,000 times, you see something like this. And this shape here is what's called the Gaussian distribution. It's kind of introduced in the 19th century. Which always shows up, right? Like so here it was the example where I kind of added up, I did 100 coin tosses, and I looked at how many of them went up heads. In some sense, it means that I added up 100 independent copies of a random quantity, which is either 0 or 1, depending on whether I got heads or tails. Right, so, but it doesn't matter whether it's that particular random quantity, right? So you can add up basically any kind of random quantity as long as they're independent or sufficiently independent, and they're all more or less the same size. There's not sort of one of them that's really much bigger than all of the others. If you look at the distribution of the sum, it's always going to follow some kind of curve like this, right? So that also kind of gives us some kind of starting point, like in the sense that very often, in a way, the type of mathematical problems that are interesting for probabilists are often problems where, in some sense, you're looking at some class of models where the actual details of the model shouldn't really matter too much. And what you're interested in is in seeing, the kind of probabilities that you can compute that in the end don't really depend too much on the details. Okay? Like here, so you're interested in this Gaussian distribution and not somehow in the exact details of what happens if you add up 50 independent quantities of a certain type, right? Because that's going to be very close to this and not exactly this, and it's going to be very much dependent on which quantities you're talking about. Okay, now this is all good, right? And hopefully it's somewhat clear. One has to be a little bit careful when actually sort of applying this to real world situation. Okay, so here's a sort of nice example that I kind of like. So it's some sort of imaginary game. So imagine that I have two envelopes, and the only information that you have, both of them contain some money. They look completely identical. the only information you've got is that one of them has twice as much money than the other one. Okay? And then you can choose one of the two. So you pick up the one you want, you open the envelope, and you see some amount of money, right? Like say 10,000 yen. And then I give you a choice, right? So you have that money. Either you can keep the money, or you can take the other envelope and take what's in the other envelope. But of course, once you open the other envelope, you have to stick to it. Like if it's less, then you cannot go back, obviously. And so then the question is, what should you do? Right? So in the other one, either there's twice as much, or there's half as much. So now, by symmetry, you think, well, since, as far as everything's concerned, these are just all completely equivalent things, well, that should be probability a half, that's probability a half. So on average, how much is in the other envelope? Well, there's a half probability that there's half the amount, and there's a half probability that there's twice the amount. So on average, there's 5/4 of the amount. 5/4 is bigger than 1, so you should always switch. But you knew that before you even looked at the first step, right? Like that calculation always works, whatever that value is. So you don't even need to look at the first envelope you pick. You should always have picked the other one. That means that you could have picked that one in the first place, right? So what's going on here? Right? Does anybody have an idea of why, why do you get some kind of paradox here? So one thing, it's kind of a relatively subtle thing, but one thing is that, implicitly we have assumed here that these are kind of all kind of equivalent situations. But that's not the case because for several reasons. So one is that actually there simply doesn't exist any probability distribution that gives the same probability to infinitely many values, right? But then that's maybe sort of a mathematical explanation, which is maybe not super satisfactory. The better explanation is maybe, very often in mathematics, when something seems surprising, then in order to kind of understand where your intuition goes wrong, it's helpful to replace some of the numbers by very large numbers, right? So what if I replace that 2 by 1,000, right? So now, exactly the same thing as before, 2 envelopes. The only information you have is that one of them has 1,000 times more money than the other one, right? Now, suppose that so same game as before, you open the envelope, and you open it, and you see 1,000,000 yen. Now, are you going to switch? Obviously not, right? Because there's no chance that I'm going to give you 1,000,000,000 yen. Right? So maybe 1,000,000, just about somehow, right? But no way I'm going to give 1,000,000,000. So it's not true that different values are equivalent, right? 1,000,000,000 yen is really not equivalent to 1,000,000 yen, right? So for those of you, so by the way, so for the mathematicians or the probabilists, you can come up with, you put this actually, say, as a proper probability distribution on, say, inverse powers of 2 or powers of 2. If you take sort of power laws, you can actually put a distribution so that that paradox still holds, but then it would have infinite expectation. And so it's sort of a paradox about, taking conditional expectations of something that has infinite expectation, and then of course you're not allowed to do that. Okay, but so here, this is sort of a funny little paradox. It can be, getting these sort of very basic probability models wrong in applications in real life can actually have like really serious consequences. So there was a case in, I don't remember what, it was like in the early 2000s or something, in the UK of a lady called Sally Clark. And so she had a baby, and the baby died of sudden infant death syndrome, which sadly sometimes happens. But then 2 or 3 years later, she had a second baby, and the second baby again died of sudden infant death syndrome. And so then neighbors were getting suspicious. They thought this is very unlikely, and so maybe she murdered the 2 babies. And so she was accused of murdering her 2 children, basically just on the basis that this was extremely unlikely. And so it went to trial, and they had an expert witness who was a medical doctor and not a statistician. And so he gave expert testimony that said, well, if you take, a family from this socioeconomic background in this part of the UK, and you look at the statistics, the probability that a child dies of sudden infant death syndrome is about 1 in 20,000. And therefore, the probability that 2 of them die of infant death syndrome is, well, 1 in 20,000 times 1 in 20,000 is 1 in 400 million, which is extremely unlikely, and therefore she probably murdered her children. And so she was actually convicted of murder on the basis of that expert testimony, and she spent several years in jail. And then, of course, her defense brought in proper statistician, who, of course, destroyed the expert testimony because there are 2 huge mistakes in there, right? So the first mistake is that I mentioned to you that the probability of 2 events happening is the product if they're independent. There's no reason to expect that this is independent. There might very well be a genetic component to sudden infant death syndrome, and of course the 2 children have the same parents, and so they have a big common genetic component. The other thing is that 1 chance in 400 million sounds very unlikely, but there's 70 million people in the UK, and there's 10 billion people in the world. So the chance that it actually happens somewhere in the world at some point is really not very small at all, right? Because you just need to try about 400 million times before you have about an order of 1 chance of this happening. And, if you look at over, I guess about 4 or 5 years, that's about the number of kids that are born in the world. And so this would actually, you would expect this to actually happen about once in every 4 or 5 years worldwide. So even though it looks like a very small probability, when you scale it up to the size of the whole world, it's not actually that small. Right. So, but now I want to go back to this second, right? So that was sort of about the symmetry thing. So I wanted to go back about the second principle for coming up with probabilities, which is universality. And so I talked about the central limit theorem, but here in the workshop that we just had this week, so we're interested in probabilities not just about random quantities, but about like random functions or random processes. And so one of the most famous ones was actually discovered somehow in the about late 18th century, actually, by Jan Egenhuis. But then it was really described more by Robert Brown, and somehow the name that stuck was actually that of Brown. And what Brown did, actually, I thought I have a movie here, but okay. Seems like this doesn't want to run. Okay, so this is supposed to move. So imagine, so what he was looking at under a microscope, so he was a botanist, okay? He was not a mathematician or a physicist. So he was a botanist. He was looking at kind of pollen, actually even like smaller particles than pollen, but basically think of pollen that he was looking at it under a microscope. So he just looked at it and he saw if the movie ran, you would see that these particles, they kind of move around and they do some sort of jittery motion like this. So he looked at the microscope, he saw that all of these particles do some sort of little motions like this. And he was wondering what's going on. And so in the beginning, he thought, well, maybe they're alive, right? So maybe these are actually like little bacteria or something like this. But then he, left the thing for a week in a cupboard or something so that there's no, no food or no nutrition or anything. And they took it out a week later and looked at it, and it still did exactly the same thing. And so clearly it's not that these things were alive. And so it actually stayed a mystery for a while. So it's kind of funny. So it seems apparently in the sort of early 19th century, that was around the time of just after the Industrial Revolution. And so in the UK, there started to be a relatively wealthy middle class. And so there were a number of people who had, in some sense, quite a bit of leisure time, right? So that was also where you started to have like sports coming up and stuff like that. And so then, this became some sort of a mystery that the general public really sort of knew about. And so in the, fancy cocktail parties of the sort of UK higher middle class society, it was sort of a topic of conversation of, what causes Brownian motion. So there's this Brownian motion that was observed by Brown, and he had no clue where it came from. And, people were sort of discussing what could possibly cause this. But then sort of, by a few decades later, people had figured out, because you see, remember, at the time, it wasn't clear at all how matter is made up, right? So it wasn't clear at all that matter is made up of atoms and stuff like that. And sort of by the late 19th century, most people were actually convinced that matter is made up of atoms and molecules, but they still didn't have a, like a completely conclusive experiment that demonstrated this. But then by that time, they kind of figured out that, yeah, so if matter is made up of molecules, then the water molecules, they would sort of bounce around. They're a little bit like little billiard balls. They sort of bounce around in all directions and sort of bounce off each other. And then the motion that you see, it's really, you have these heavy bit of pollen, and then you have these water molecules that kind of bombard it. And every time it gets hit by a water molecule, it moves, it gets a little shock in one direction. And of course, each water molecule is really tiny and doesn't really move it much, but there's many, many, many of them, right? And there's so many of them that all together, it actually produces a motion that you can really observe under a microscope. And then in the very early 20th century, two physicists, so Einstein and Smoluchowski, you've certainly heard of Einstein, they came up with a more quantitative kind of, right? So they came up with this picture. So this picture was already sort of understood at the time, but they came up with a more quantitative prediction, if you want, of not just why it moves, but also how fast it should move. And in particular, from a mathematical point of view, the prediction that they came up with is that if you imagine that you follow one of these particles, right? So you see it somewhere at some instant of time, and then say you close your eyes and you try to predict where it is a second later. So then a second later, it's going to be at some random location. But then you would want to ask, what is somehow the distribution of this location? What's the probability distribution of this location? And what they came up with is that there's a PDE that describes how this distribution evolves with time. And that differential equation is actually the heat equation. So it's exactly the same equation as the one that describes how heat propagates in a solid, right? But here it's probability that propagates, if you want. And it came with sort of quantitative predictions, which Perrin then a few years later actually, so he did the actual experiment. He didn't use pollen, but kind of gouache, which is like water paint, if you want, the little tiny particles in the salt water paint. And it really matched the prediction. I mean, it matched the prediction to within whatever, 10% or something like this. But it was certainly good enough to show that the prediction was valid. And that at the time, it was really the first time that there was a prediction that relied on the atomistic nature of water and so on, which couldn't be described or couldn't be explained in any other way. Okay, so if you want, that was somehow the first really conclusive experiment that demonstrated the existence of atoms. And so that's why Perrin then got the Nobel Prize for that in 1926. And what's interesting is that about the same time, there was a young Frenchman called Bachelier. He was interested in something completely different. So he was interested in understanding how stock prices evolve, right? So he was interested in, say, you take whatever, you take a share of IBM or something, and then you look at the price of IBM and it kind of moves around in a certain way. It seems kind of random. And so he wrote a thesis on this topic in 1900, which in some sense was really kind of in advance of its time. And the French mathematicians at the time, in some sense, didn't actually like it too much. They thought it was, not a very elegant topic for a mathematician to look at. It sort of seemed a bit dirty and a bit too applied. And so he really had trouble getting a job. So he actually did get a job at the Sorbonne in the end, but then World War I broke out. And, well, he had to go to fight. And when he came back, the job was gone. And they didn't want to give him a job anymore. And so he basically spent most of his time basically just tutoring rich kids for high school, I suppose, or something. In the end, he got a job in, I think, Bordeaux, maybe, or something like this. But it was, when he was in his late 50s or something like that. But anyway, so the point of his thesis was that he had a description of how stock prices change, which was very similar to the story I just told you about the Brownian motion, except that replaced the pollen by, say, the share price of IBM, and replaced the water molecules by people who buy and sell these shares. Right? The idea is to say, well, every time somebody sells shares of IBM, that pushes the price down a little bit. As every time somebody wants to buy shares of IBM, that pushes the price up a little bit. And of course, if you and I want to buy a couple shares, that has essentially no effect. But there's a million people that are going to buy and sell shares all at the same time, all the time. And so there are lots of these effects that go in both directions, and they kind of add up. And that's what causes this jittery, random-looking motion. Okay? And the interesting thing is that he also had a formula that predicted the probability distribution of the shares at a later time. And he also figured out that it's described by the heat equation. So exactly the same equation as before, which then kind of laid foundation for Black-Scholes. And he somehow never got anything out of it. They got a Nobel Prize out of it. So he was really kind of unlucky in some sense. But the point here of this little story is that you see these two completely different situations. On the one hand, you have sort of pollen that Brown is observing under the microscope. On the other hand, you have like the share price of IBM. Well, obviously it wasn't IBM at the time. And you end up having the same mathematics that actually describes both. Okay? Because somehow the story behind it is the same, but the details of the story are different. Right? So that's what we talk when we talk about universality. It's really that, right? Like you have two similar stories that then produce basically the same math when you look at what happens on larger scales, but the details of what happens, at fine scales is quite different in the two stories. And then this, by the way, so somehow later on, like the proper mathematical foundations for, Brownian motion or stock prices and so on. So that really kind of came with Wiener, and then also Donska. So they describe, so let me actually show you sort of a movie here. Right, so here, So what Wiener described, so he really constructed a proper mathematical model for this Brownian motion. And so this model is a probability measure on a space of continuous function. And what I've done here is I take a random function, which is random according to that particular probability measure, and then I plot it, and here I'm just sort of zooming out. Right? And you see that, this thing moves, but it always kind of looks the same. Right? So you get some kind of fractal random function that in a way kind of looks more or less the same at every scale. And that's this Brownian motion. And by the way, this kind of inverted parabola here, it's the parabola which is left invariant by my scaling. So the way you have to kind of zoom out is when you zoom out by a factor 2 horizontally, you zoom out by a factor square root of 2 vertically, not 2. Okay, so you kind of squeeze, you sort of zoom out at different speeds in both directions, right, in such a way that that parabola stays the same. Okay. Right, and so now in the last, sort of last 15 minutes or so, I want to talk about a bit more about sort of more recent kind of mathematics that goes a little bit in this direction, right? So what I've been talking about so far is essentially, 19th century and first half of 20th century kind of mathematics. And so a recent piece of mathematics, which is in some sense has very close similarities to this story of Brownian motion, is the study of, it's called interface growth models. So here the context is, think of something like a forest fire. So actually I've got a movie here of something. So here, what you see in the movie is, you see that there's this kind of fluff on the ground, right, so that you get in spring. And somehow it was set on fire. And so here you have that fluff that's kind of burning. And so you have this flame front here. And what you see is that the flame front is more or less straight, right? But, okay, let's show again here, right? So it's more or less straight, but you see it has these kind of random fluctuations here, right? And the same happens here, right? So like this is a forest fire, a picture of a forest fire from somewhere, in, I don't remember where. And you see you have this flame front, and it's not quite smooth, right? It's not flat. So you have these fluctuations here, where there are some bits where it kind of moves a bit faster, some bits where it moves a bit slower. And so you're interested here in some, ask yourself, what is the sort of idealized mathematical model that describes the motion of these flame fronts? So now this is not just, remember, Brownian motion was basically just a function of time. Now you have something which is sort of a function of time and space. And there are other kind of situations of the same type, right? So like similarly to the fact that for Brownian motion, there was the story of the pollen in the water, and there was the story of the stock prices, and it's sort of the same story, but in a different context. And here too, so here what you see is a picture of an experiment where people take a liquid crystal, so like the one you used to have, or you have in a sort of, think of like an old-fashioned pocket calculator, right? And you have these LCD display. And so you have a liquid crystal that comes in two different phases, and they have two different optical properties. So, and then it shows up as basically either black or gray. And one of them is more stable than the other one. And so here it turns out that somehow the gray one is less stable and the black one is more stable. And so what you do is you prepare it in the gray one, which is the less stable one. And then you take a laser beam and you sort of zap the laser beam on the display. And then the laser beam kind of gives it some activation energy. And so that makes it switch kind of from the unstable to the stable phase, which is the black. So basically, you're painting a black line onto that screen with your laser. And then that black line, because it's more stable, it gets wider and wider. Right? And so you have this sort of black line that you paint on the screen, and then it gets wider and wider. But if you kind of zoom onto the boundary of that black line, you see something like this. You see that it's not quite straight, but you also have these kind of random fluctuations. And of course, it's for sort of the same reason that you have these random fluctuations for the flame front in the forest fire, right? Like some bits are going to kind of flip over a bit faster, some are going to flip over a bit slower. And so that kind of maybe depends on the details of how the molecules of that liquid crystal are arranged at a given position at a given moment, right? And you can also come up with sort of just pure toy mathematical models that are kind of similar. So one of my favorite model of that type is sort of the Tetris model. So what you do here is you sort of play Tetris without playing it, right? So you imagine, so here you see these are just Tetris bricks. And imagine you have Tetris bricks that are kind of falling down, and they just pile up. So you don't do anything to try to make them fit well or not. And okay, that looks like it has nothing to do with what we just saw. But if you actually zoom out, right, then it really kind of starts to look the same. So you see here, you run it, so you have like millions of Tetris bricks that fall down super fast. And now you have this kind of interface here, right, between the bit here where you have Tetris bricks and the bit here where you have no Tetris bricks. And this bit kind of moves up, right? And again, it's not straight. You get some kind of a random surface of it like that. And again, you'd imagine that, you can imagine that the mechanism is somewhat similar, right? Like the story of how this moves is a bit similar to the story of how, the liquid crystal kind of thing moves up. Like some bits are going to just by random fluctuations, some bits are going to move a bit faster, some are going to move a bit slower, and so on. And so here, well, you can come up with various models like that. It turns out that there's been only very recently, so it's about 10 years ago, there was an article by Matetsky, Kostel, and Vremenik where they gave a mathematical description of the object that you expect to describe these situations, right? So like there's some kind of random space-time process. And again, just like Brownian motion, you can give a complete description of it. It's just the description is much more complicated than the description of Brownian motion. And unlike Brownian motion, so in the case of Brownian motion, by now, there are many mathematical theorems that show that, many, many different kind of processes or situations converge to Brownian motion. And it's really quite well understood what are the things that you could expect to converge to Brownian motion and what are the things that you couldn't. Here in this case, it is quite well understood what are the things that you would expect to converge to this object, which is called the KPZ fixed point, and what are the things that you wouldn't. But mathematically, there's very few theorems, right? So there's like 2 or 3 very specific mathematical models for which there's a theorem, and that's because they have some very specific structure. I think we heard about some of these models this afternoon. And so it's kind of interesting is that also some of the calculations that show up for these particular models, they actually link to other areas of mathematics. One aspect of this that I've personally been involved in is that there is somehow a simpler situation where it's much better understood, where the limit at least is much better understood, which is the one where imagine a similar kind of situation where you have a one-dimensional interface that separates 2 regions. But now, in all the examples that I showed you so far, the interface only moves in one direction, right? So like the fire, it can only move in the direction of the things that haven't burned yet. It doesn't move backwards into the stuff that has already burned, right? Same with the Tetris bricks. They just pile up. They don't disappear. So it only goes in one direction. But you can imagine similar kind of models where things can go in both directions. Right? And so you can imagine somewhere it's actually completely symmetric, whether you go in one direction or the opposite direction. And for these very symmetric models, there it's actually well understood what is the limit that you get when you look at what happens at very large scales. And then you can ask yourself, what happens if you look at something which is almost symmetric, but not quite, and you kind of start zooming out at very large scales. And then what you expect is that as you zoom out, in the beginning, it looks more and more like the limit that you would get as if it were symmetric. But then at some point, if you zoom out sufficiently, you start to actually see the effect of the asymmetry, and then it should kind of, the behavior should change, and it should look like this KPZ fixed point. And so there should be at some point, a moment where it changes behavior, and then you can ask yourself, what does it look like at that point where it's sort of at the scale where it kind of changes behavior? And there, what you have is, well, Kaldar, Parisi, and Zhang in the 80s, mid-80s, they proposed some stochastic partial differential equation that's supposed to describe what happens at that kind of intermediate scale in these kind of situations. And okay, so I'm not going to go into the details of sort of what that equation means, but the point here is that, so there's one term here that describes, if you want, sort of random fluctuations, and which is very irregular. And so solutions to this equation are going to be extremely irregular, and so irregular that they actually don't have a derivative at any point. And so this term here doesn't have any meaning, right? So here, that's the square of the derivative. And so if it doesn't have any derivative, or the derivative is kind of infinite at every point, then what does it mean to take the square, right? I mean, it's just nonsense. It's just infinity at every point. And so in some sense, there should be some kind of infinite constant that should be subtracted here so that the equation has some meaning. And so that's something that by now it's sort of a relatively recent theory, sort of developed over the last 10 years. So now we actually understand quite well what these type of, how do we interpret mathematically these type of equations. And you can really derive them from sort of more realistic models. So here's an example. So if you think again about the flame front, like what would be a good model of how that flame front moves, right? So think you put yourself at the point on the flame front, sort of moves in the perpendicular direction here. And then it's going to move at what speed is it going to move? So there's some kind of average speed at which it burns. And let's just say that that's 1, right? I mean, I can choose units whichever way I want, so I make that average speed 1. Then there's the thing that, like, you can kind of imagine that if you're here, then it's going to move kind of faster, right? Because there's more flames somehow close to it here, so it's already kind of a bit hotter on the sides. And so you can kind of imagine that here it's going to move up a little bit faster. It's going to burn a bit faster. Whereas, say, here, for example, it's going to burn a bit slower, right? Because the other flames are sort of a bit behind. And so it's quite natural to subtract the term here, which is essentially, which gets larger if the thing is very curved and is smaller when the thing is very flat. So one way of doing it is you sort of, take the circle that matches best that point, and then you add a term which is proportional to like 1 over the radius of that circle. Right? So here the circle is small, so 1 over the radius is big. Here the circle is big, so 1 over the radius is small. And then this is either positive or negative, depending on whether it's concave like this or convex like that. Okay? And then there's a term which says, well, some bits are going to burn a bit faster, some bits are going to burn a bit slower, right? Like depending on what kind of, what the forest looks like in the different locations. And so that's just some function which depends on the location which you fix. That's somehow the shape of your forest, if you want. So that's a function of this two-dimensional plane, which is going to be kind of random. And here, the regime that we're looking at is the one where we assume that this is a relatively small effect. So we put some kind of small parameter in front of that. And then you can, write down the equation that this satisfies, and you get some kind of complicated equation like this, which looks a little bit similar to this KPZ equation I wrote on earlier, but not quite. But actually, you can prove, so that's a relatively recent result we got a couple of years ago with 2 PhD students of mine. You can show that if you take the solution to this equation and you start with something kind of flat, and you look at what happens at very large scales, then it does actually converge to a solution to this KPZ equation. Right? So that's some kind of, not a proof of universality, but at least it's an illustration that this equation has some kind of universal feature, right? Because I started from a model which seemed quite reasonable, which didn't a priori have anything to do with that equation. And if I actually look at the behavior at large scales, I really see that equation appearing. So, okay, I think, well, okay, I'm not going to, I think I should probably stop here. It's probably a good point to stop. So thank you very much.